Hello guys, how are you doing? So, well, there come a moment to the life of a mouse when you think, I have to derive Kepler's orbits by myself. Yeah, it's a very serious time in your life. So, well, let's do it. Yeah, yeah, thank you. So, let's think. Let's say there is some planet of mass m, m sub e, yeah, like Earth. And then there is another object, mass m, yeah. So, and then from the center of there is a vector joining them, vector r, yeah, from the center of the big planet. Uh, so, then what is the force, gravitational force between them? Well, this force will be the force of m sub e over m lowercase will be minus r hat unitary vector times g, the gravitational universal constants, the product of the masses over the radius to the square, r square. Yeah. So, just to simplify things, we will assume that the center of mass of the system lies in the center of the big planet. Yeah. So one possibility for this is that m sub e is much larger than m. Yeah. So then the center of mass is here at the center of the big planet. Yeah. So it's just a simplification. In principle, we should do the calculations with respect to the center of mass, but the result will be very similar. Yeah. So then we will write the third Newton's law. M times the acceleration, yeah, equals the force. Yeah, and the force in this case is minus r hat g m sub e m over r square. Yeah. So we will constrain our calculation just to the plane. Yeah. So we will use polar coordinates. Yeah. We use polar coordinates. Yeah. So we will have r unitary r equals cosine of theta times sin of theta. Yeah. Unitary hat angle equals minus sin of theta comma cosine of theta. Yeah. So this is the following: have x, y, and then we have r. This is theta. Yeah. And r equals r hat. Yeah. So, well, in this system of coordinates, the acceleration of the mass m, yeah, can be written as the following. Yeah, this is just taking derivatives. There is nothing deep inside this, so I will just write it down. Yeah, there is a lot of dots. Dots are time derivatives. Yeah, it's not German, it's time derivatives. Yeah. Okay. So this is the radial component of the acceleration, and this is the angular component of the acceleration. Yeah. So, and then we will equal the forces. Yeah. So we'll have m times the acceleration equals minus r hat g m sub e and lowercase r square. Yeah, we can simplify the small m. Yeah, and then we will equal the radial and angular components. So we'll move a bit our whiteboard up. So, and then we will equal the radial part. So we got r second derivative minus r theta dot square equals minus g m sub e over r square. Then the angular, we'll equal now this term. So on the right side of the equality there is nothing. Yeah, so we can put just 0 times theta, unitary theta. So r theta double time derivative plus 2r dot theta dot equals 0. Yeah. So we will call this one equation 1, this one equation 2. Yeah. So, well, we have done nothing, just write down the dynamical equation. Yeah. So, by components. So now we will work on each of these equations. Yeah. First, we will work a bit on the angular part. Equation 2. Yeah, we got r second time derivative of theta plus 2r dot theta dot equals 0. We will multiply this by r. Yeah. So this is the same as r square theta dot dot plus 2r r dot theta dot equals 0. Yeah. So I know you are very smart. No, you already noticed that this is the same as d to the t of r square theta dot plus that's nothing equals 0. Yeah. So we will multiply now by m. So we got d to the t of m r square theta dot equals 0. Yeah. So, well, this is the time derivative of something. of a function, if the time derivative is 0, it means that this function is a constant, yeah? And this is just the angular momentum. M r squared theta dot equals L, yeah? And this is the angular momentum. It's conserved. Wow! Wow! Very, very important. Angular momentum. So we will use a lot this formula. We will write it in another way. Yeah, we will write it theta dot equal L over M R square. Yeah, we will say that this is formula 3. Yeah. Okay, now we will go back to our first equation. 1. Yeah. Equation 1, if you remember, was r second minus r theta dot square equals minus gm sub e over r square. So now we will replace theta dot with L over m r square. Yeah. So we got r the second time derivative minus the square of this. Yeah. So we will get L square over m square r to the 4th. So, and then we have an r on top, so they will cancel, we'll get just r to the cube. So, minus 1 over r cube L over m square, yeah, equals minus g m sub e over r square. Okay, this is looking good. Yeah, we will call this one 4. Yeah. So this equation, now we got the second time derivative of r as a function of r. Yeah. So it looks something that we can work with, but it's not that simple yet. Huh? So we could multiply this, for example, by r dot. Yeah. And then we can write this as a derivative of something else. Then we will get the mechanical energy. Yeah. So that's one way. Another way is the following. Yeah. So we would like to express the second time derivative of r as a function of the derivative on theta instead of the time. Yeah. So we want to pass from a dependence on r of t, yeah, where t is the time, to a dependence on r of theta. Yeah, so we want the orbits independent of time. Yeah. So well, let's just do this. Yeah, let's say that r equals f of theta. Yeah. So then we would like to replace this second time derivative as the derivative of on theta instead of the time. Yeah. So we will do the following. Then first we calculate the first time derivative of r. It will be the d to the t of f. Yeah. So it will be the same as the f to the theta times the theta to the t by the chain rule. yeah? So this is the same as f prime times theta dot, yeah? Then we will use equation 3. You remember equation 3? Let's say theta dot equals L over m r square. In this case, theta dot equals L over m f square. Yeah? So then r dot equals f prime, yeah, over f square times L over m. Yeah? So we can rewrite this as minus, yeah, d to the theta of 1 over f L over m. Yeah? So, well, our change, our assumption, yeah, is leading to something, but we are getting something very complex, yeah? We are getting, we are not simplifying the equation, we are simplifying, we are making the equation worse, yeah? So, from here we see that we are getting r dot, the first time derivative of r, as a function of the derivative of 1 over f. Yeah? So, instead of using r equal f of theta, we will get something better if we use instead r equal 1 over g of theta. Yeah? So, we have to find out better. Yeah, let's see. So in this case, r dot equals d to the theta 1 over g, yeah, times d theta to dt. Yeah, this is the same as minus 1 over g square g prime. Yeah, but here is the magic. Yeah, because we have theta dot. Yeah, but theta dot is, in this case, theta dot equals L over m r square. Yeah, but when we will replace r equals 1 over g, then theta equals L over m g square. Then this will simplify the g square. So r dot equals minus g prime L over m. Yeah? Wow! Very nice! So this will be equation 5. Okay, we're going very good. Now we are just very close to calculate the second time derivative. So now we'll rewrite here r dot equals minus g prime L over m. Yeah, so much better than before. Then we got r prime equals f of r dot equals f prime over f square L over m. Yeah, do you see the difference? Much simpler here. So this is no good. No. So the second time derivative, r second equals dr to dt, dr dot to dt equals, yeah, minus G prime second G double prime times theta dot L over M. Yeah? We will replace again. Theta dot equals L over M R square equals L over M G square. Yeah? So, second time derivative of R equals minus G double prime times G square times L over M square. Yeah? Okay. Let's finally remember our equation for R. Equation 4 was R second time derivative minus 1 over R square L over M square equal minus G M sub E over R square. Yeah? So we will replace R equal 1 over G. Yeah? So here we get minus G prime double prime mg square L over M square minus G cube L over M square equals minus G M sub E G square. Yeah? Magic! Yeah, you see. The G squares cancel. So, we cancel also the negative signs. So, and we will also multiply by L, by M over L square. So, finally we get G double prime plus G equals G M sub E L over M over L square. Yeah? Wow! This is a very nice equation now, you see. Because yes, this is just the simple harmonic oscillator equation with a constant source term. Yeah? So, this will be equation 6. Yeah? So, this equation is quite simple to solve. Yeah? Yeah. This harmonic equation we'll write here again. It's just 6 G double prime plus G equals G uppercase M sub E M over L square. Yeah? So, the solution to the homogeneous part, so you will take this part as 0, yeah, is just the following. The homogeneous is G sub H equals A times cosine of theta plus phi, where phi is just a constant. Also A, arbitrary constants. We will determine them then later. And it's easy to see also that the particular solution, one particular solution is G sub P yeah, it's trivial because G sub P just can be G M sub E M over L square. Yeah? If you replace this on in the equation 6, you will get the dissatisfied equation 6. Yeah? And this and then the final solution will be g equals g sub h plus g sub p. Yeah, so it will be g m sub e m over l square plus a cosine of theta plus v. Yeah. Wow, very simple, no? Okay. So, then we can factor. Since a is an arbitrary constant, we can rename it. Yeah? So we can factor this as g m sub e m over l square times 1 plus epsilon cosine of theta plus phi. Yeah? And then we can write r equals 1 over g equals 1 over g m sub e m over l square over 1 plus epsilon cosine of theta plus phi. Wow! And this is the Kepler orbits. Yeah, this is represent either circles, ellipses, parabolas, or hyperbolas, depending on the value of epsilon. Yeah. So it's very easy to see. You can do it. If you replace back the polar coordinates to Cartesian, yeah, if you make the replacement, for example, x equal cosine of theta, y equals sine of theta, then you will get for epsilon equals 0, we get a circle. For epsilon more than 0 and less than 1, you will get an ellipse. For epsilon equals 1, you will get a parabola. And for epsilon more than 1, you will get an hyperbola. Yeah? So, well, that's it. Yeah? I hope you like it. So, I will leave you with some graph of these orbits. Yeah? So, well, I just have to show you how I made this graph. Yeah? So, we got the equation for the angular momentum theta dot equals L over m r square. Yeah? So, and this is the same as L over m times 1 plus epsilon cosine of theta plus phi. Yeah, over 1 over g m sub e m over r l square. All of this is square. Yeah? So, then you can write this as theta dot over 1 plus epsilon cosine of theta plus phi equals some constant. Yeah? Yeah. So then this can be separated. Theta over 1 plus epsilon cosine of theta plus phi equals this constant, I will put just c, yeah, times dt. Yeah, you can integrate this. Yeah, and then with this you can get the angle as a function of time. Yeah, or the contrary, the time is a function of the angle. Yeah, so this way you can see how fast the planetoid moves. Yeah, and you see in the animations that follow. Okay, see you. I hope you like it. Bye.